Hello and welcome to Math Zone African Motives. Today, we're diving into a crucial topic in calculus, integrating algebraic fractions. This is Unit 4.6 on integration of algebraic fractions. By the end of this video, you will be able to determine the best method to integrate a given algebraic fraction and apply those methods step by step to find the solution. You'll learn the criteria for using substitution, long division, and partial fractions, and see them in action with several examples. Let's first understand the general principles. When you have an integral of an algebraic fraction, you need to look at the degrees of the numerator and the denominator. First, if the degree of the numerator is less than the degree of the denominator, you might be able to use substitution or, in some cases, partial fractions. This is a key indicator that a simpler method might work. The numerator is a simpler polynomial than the denominator. Second, if the degree of the numerator is greater than or equal to the degree of the denominator, you must first perform polynomial long division. This breaks the fraction into a polynomial plus a proper fraction, which you can then integrate. This rule is non-negotiable. If the top is heavier than the bottom, you must divide first. Let's see these rules in action with our first example. Our first problem is to determine the integral of the fraction x plus 2 divided by x minus 3. Let's apply our rule. The numerator is a linear polynomial degree 1. We can see the degree is 1. The denominator is also a linear polynomial degree 1. The degree of the denominator is also 1. Since the degrees are equal, the degree of the numerator is not less than the degree of the denominator. Therefore, we must use polynomial long division. Let's perform the long division. We are dividing x plus 2 by x minus 3. Here we set up our division, with the divisor on the left and the dividend under the bar. We ask, how many times does x go into x? The answer is 1. We write 1 above the x in the dividend. Now we multiply this 1 by the entire divisor x minus 3 to get x minus 3. We place x minus 3 under the dividend and draw a line. Next, we subtract. Remember to distribute the minus sign. We have x minus x, which is 0, and 2 minus negative 3, which is 2 plus 3, or 5. Our remainder is 5. Since 5 is a constant and x minus 3 is a polynomial of degree 1, we cannot divide any further. We can write the result in the form, quotient plus remainder over divisor. So our fraction becomes 1 plus 5 over the quantity x minus 3. Now that we've used long division, we can go back to our integral. We substitute our new expression for the integrand. The integral of x plus 2 over x minus 3 dx is now the integral of the quantity 1 plus 5 over x minus 3 dx. We can split this into two separate, simpler integrals using the sum and difference rule for integrals. This gives us the integral of 1 dx plus 5 times the integral of 1 over x minus 3 dx. We can pull the constant 5 out of the second integral. The integral of 1 dx is simply x. For the second integral, we can use the substitution method. We'll let you equal the denominator x minus 3. Taking the derivative, do is simply dx. Substituting this back into the integral, we get 5 times the integral of 1 over u do. The integral of 1 over u is the natural logarithm of the absolute value of u. This gives us x plus 5 times the natural log of the absolute value of u, plus our constant of integration, c. Finally, we substitute back u equals x minus 3 to get our final answer. X plus 5 times the natural log of the absolute value of x minus 3 plus c. Let's check this with the provided memo. The memo gives us the same answer, verified using memo. Next up is problem 2. We need to integrate the quantity x squared minus 1 divided by x squared plus 1. Again, let's check our degrees. The numerator is degree 2. Degree of the numerator is 2. The denominator is also degree 2. And the degree of the denominator is also 2. Since the degrees are equal, the numerator's degree is not less than the denominator's. So, we must use long division. Let's perform the long division. We're dividing x squared minus 1 by x squared plus 1. We set up our division. How many times does x squared go into x squared? The answer is 1. We write 1 above the x squared term. Now we multiply 1 by the divisor, x squared plus 1, to get x squared plus 1. We place this under the dividend. Next, we subtract. Remember to distribute the minus sign. We have x squared minus x squared, which is 0, and negative 1 minus 1, which is negative 2. Our remainder is negative 2. Since the degree of the remainder 0 is less than the degree of the divisor 2, we stop here. Writing this as quotient plus remainder over divisor, our fraction becomes 1 plus negative 2 over the quantity x squared plus 1. This can be simplified to 1 minus 2 over x squared plus 1. Now we can integrate. We replace the original fraction with our new expression. The integral becomes the integral of the quantity 1 minus 2 over x squared plus 1 dt. Again, we split this into two simpler integrals. This gives us the integral of 1 dx minus 2 times the integral of 1 over x squared plus 1 dx. The integral of 1 dx is x. The second integral is a standard form. This integral is 1 over x squared plus 1 squared. This is the arctangent or inverse tangent rule. The general formula is the integral of 1 over a squared plus x squared equals 1 over a times the inverse tangent of x over a plus c. In our case, a squared is 1, so a is 1. X squared is x squared, so x is x. Applying the formula, we get x minus 2 times the inverse tangent of x, and of course, plus our constant c. Our final answer is x minus 2 times the inverse tangent of x plus c. Comparing this with the memo, we see it matches perfectly. Verified using memo. Moving on to problem 3. We need to integrate 4x minus 6 divided by x squared minus 3x. Let's check the degrees. The numerator is degree 1, 4x minus 6. The numerator is degree 1. The denominator is degree 2, x squared minus 3x. The denominator is degree 2. In this case, the degree of the numerator is less than the degree of the denominator. This tells us we should try substitution. Our goal is to find a function in the denominator whose derivative appears in the numerator. Let's test the substitution method. We'll let you be the denominator. So let u equal x squared minus 3x. Now we need to find do by taking the derivative with respect to x. The derivative of x squared is 2x, and the derivative of negative 3x is negative 3, so do equals 2x minus 3 dx. Now let's compare our numerator 4x minus 6 with du, which is 2x minus 3. Notice that the numerator is exactly 2 times do. This means our substitution will work perfectly. We can rewrite the integral by factoring out a 2 from the numerator. Now we substitute u and do into the integral. The integral becomes 2 times the integral of do over u. This is one of the most fundamental integrals. The integral of 1 over u is the natural logarithm of the absolute value of u. So we have 2 times the natural log of the absolute value of u plus c. The final step is to substitute back the expression for u. Our final answer is 2 times the natural log of the absolute value of x squared minus 3x plus c. Let's check this with the memo. The answer matches. Verified using memo. Problem 4 is to integrate x cubed plus x divided by x squared minus 1. Let's check the degrees. The numerator x cubed plus x is degree 3. Degree of numerator is 3. The denominator x squared minus 1 is degree 2. Degree of denominator is 2. Since the degree of the numerator is greater than the degree of the denominator, we must use polynomial long division. This is the first step. Let's divide x cubed plus x by x squared minus 1. For long division, it's good practice to write the polynomials with all powers of x, even if the coefficient is 0. The dividend is x cubed plus x, and we can write the divisor as x squared plus 0x minus 1. Now we set up the division. Here's our setup. How many times does x squared go into x cubed? The answer is x. Multiply x by the divisor, x squared minus 1, to get x cubed minus x. Place this below the dividend. Now subtract. Remember the minus sign distributes to both terms. X cubed minus x cubed is 0. X minus negative x is x plus x, which is 2x. We bring down the other terms if there were any, but here we just have 2x. Our remainder is 2x. The degree of the remainder, 1, is less than the degree of the divisor, 2, so we stop. Writing this in the form quotient plus remainder over divisor, our fraction is now x plus 2x over x squared minus 1. Now we integrate our new expression. The integral is now the integral of x plus 2x over x squared minus 1 dx. We split this into two integrals. We have the integral of x dx plus the integral of 2x over x squared minus 1 dx. The integral of x dx is x squared over 2. For the second integral, notice the numerator is exactly the derivative of the denominator. We can use u substitution. Let u equal the denominator x squared minus 1. Then do is the derivative, which is 2x dx. Substituting this in, the second integral becomes the integral of 1 over u do. This integrates to the natural log of the absolute value of u. So we have x squared over 2 plus the natural log of the absolute value of u plus c. Substituting u back, we get our final answer. X squared over 2 plus the natural log of the absolute value of x squared minus 1 plus c. This matches the result from the long division method in the memo. Verified using memo. Let's quickly look at the alternative solution provided for problem 4, which does not use long division. The alternative method for this problem is interesting, but it relies on a specific algebraic manipulation that you might not always spot. Let u equal the denominator x squared minus 1. This means u plus 1 equals x squared. From before, we know that do is 2x dx, so dx is do over 2x. Now we substitute these into the original integral. We replace x squared minus 1 with u and dx with do over 2x. We can simplify this expression, canceling one x term and pulling out the constant wahal fasa. We're left with an x squared term inside the integral, which we must replace using our substitution x squared equals u plus 1. This leaves us with the integral of u plus 1 divided by u. This is a clever and effective method when it's applicable. Now we can simplify this inside the integral to 1 plus 2 over u. This is an easy integral to solve. However, as the memo notes, using long division first is generally a more systematic and reliable approach for these types of problems. Problem 5 involves a cubic polynomial in the numerator divided by a linear polynomial in the denominator. This is a classic case for polynomial long division. The numerator, x cubed plus 3x squared plus 2x minus 5, is degree 3. Numerator is degree 3. The denominator, x minus 2, is degree 1. Denominator is degree 1. Since the degree of the numerator is much higher than the denominator, we'll perform long division to simplify the fraction before integrating. Let's perform the long division. We're dividing x cubed plus 3x squared plus 2x minus 5 by x minus 2. We set up our division. First, we divide x cubed by x, which gives x squared. We write this in the quotient. So the first term of the quotient is x squared. Multiply x squared by x minus 2 to get x cubed minus 2x squared. Subtract this from the dividend. Subtracting gives 5x squared. Subtracting gives 5x squared. Bring down the next term, 2x. Now we have 5x squared plus 2x. Divide 5x squared by x to get 5. Add this to the quotient. Multiply 5x by x minus 2 to get 5x squared minus 10x. Subtract this. Subtracting gives 12. Subtracting gives 12. Bring down the last term, negative 5. Now we have 12x minus 5. Divide 12x by x to get 12. Add this to the quotient. Multiply 12 by x minus 2 to get 12x minus 4. Subtract this. Subtracting gives 19. Our final remainder is 19. The degree of 19, 0, is less than the degree of x minus 2, 1, so we are done. Writing this as quotient plus remainder over divisor. Our fraction is now x squared plus 5x plus 12 plus 19 over x minus 2. Now we integrate our simplified expression. The integral is the integral of x squared plus 5x plus 12 plus 19 over x minus 2, all with respect to x. We can integrate each term separately. The integral of x squared is x cubed over 3. The integral of 5x is 5x squared over 2. The integral of 12 is 12. For the last term, 19 over x minus 2, we can use u substitution with u equals x minus 2 and do equals dx. The integral of 19 over x minus 2 is 19 times the natural log of the absolute value of x minus 2. Combining all our terms gives the final answer. Our final answer is x cubed over 3 plus 5x squared over 2 plus 12x plus 19 times the natural log of the absolute value of x minus 2 plus c. Let's check our result with the memo. It matches exactly. Verified using memo. Our final problem for today, number 6. We need to find the integral of 2x minus 5 divided by the square of the quantity, x minus 3 times x minus 2. First, let's expand the denominator to determine its degree. Expanding the terms inside the parentheses gives x squared minus 5x plus 6. Squaring this expression, the highest power will be x squared squared, which is x to the fourth. The denominator is a degree 4 polynomial. The numerator, 2x minus 5, is degree 1. Numerator is degree 1. Since the degree of the numerator is less than the degree of the denominator, we should try the u substitution method. Let's see if it works. Let's perform the u substitution. The memo suggests letting u equal the expression inside the square in the denominator. U equals x squared minus 5x plus 6. Now we find the differential do. The derivative of x squared minus 5x plus 6 is 2x minus 5, so do is 2x minus 5 dx. Notice something amazing here. The expression for do is identical to the numerator of our original fraction. This means our substitution is perfectly set up. We can rewrite dx as do divided by the quantity 2x minus 5. Now let's substitute u and do into our integral. We replace the numerator with 2x5, the denominator term with u, so the denominator becomes u squared, and dx with do over 2x5. The 2x5 terms in the numerator and denominator cancel out, leaving us with a very simple integral, the integral of 1 over u squared do. To integrate 1 over u squared, we can rewrite it using a negative exponent. This is the integral of u to the power of negative 2. Now we use the power rule for integration. Add 1 to the exponent and divide by the new exponent. Negative 2 plus 1 is negative 1. Dividing by negative 1, we get negative u to the power of negative 1 plus c. Finally, we substitute back the expression for u. Our final answer is negative 1 over x squared minus 5x plus 6 plus c. Checking the memo, our answer matches. Verified using memo. This problem was a great example of the power of substitution. Let's quickly recap what we've learned. The most important first step in integrating an algebraic fraction is to compare the degrees of the numerator and denominator. If the numerator's degree is less than the denominator's, you should first try substitution. If that doesn't work, then you'd consider partial fractions. If the numerator's degree is greater than or equal to the denominator's, you must start with long division. Remember to always add the constant of integration, c, for indefinite integrals. That's all for today's tutorial on Math Zone African motives. We hope you found this helpful. Subscribe for more tutorials from Math Zone African motives.